we completed the magnetic field part due to the straight wires, right? That part we did, and yeah, this is the thing that we did in the last two, right? So we calculated semi-infinite wire, we calculated infinite wire, and then straight wire. So all these things we calculated, right? Now let us
Yes, sir.
now let us. Yeah, so do you remember the about Seven's law? Do you remember that? Do you remember
Yes, sir.
the Bio-Saver's law? Do you remember that?
Yes, sir.
Yeah. What does it say?
So the Biot law states that, sir,
So we are
magnetic
studying.
field, like due to a current conductor, is inversely proportional to like the square of the distance from the conductor and point.
Yeah, so you are correct. So this is mu naught I d l sine theta by r square, right? And that is mu naught by. This is the magnetic field, right? So this is
Yes, sir.
the Biot-Saver's law, and we so and then we can also write this in the vector form. So this is mu naught I dl cross r divided by r cube, and these are the things. This is the parcels, right? So remembering these things we calculated, right? Calculated magnetic field due to straight wire, and then we have these three kinds of wire, which is right. And then we also talked about the direction of the magnetic field. Direction would be given by dl cross r. So now let us talk about magnetic field of circular. Okay, so what do we have? We have a circular wire, right? We have a circular wire, and the current is flowing in, right? So let's say the current is flowing this way, and we want to calculate the magnetic field at center. So at center, we want to calculate the magnetic. So what we will do, we'll take a small length element dl, right? So the direction of dl is this, right? And then the distance, the perpendicular distance from where we are trying to calculate the magnetic field is this. This is our R, right? So the theta angle would be how much? What would be theta for this case? What is theta?
Theta would be dl.
Theta would be how much? This is dl. Direction of dl is this tangent. Direction of r is this. So what is the angle between theta and what between the dl and r? That is the theta angle, right? The sine theta is this theta is the angle between dl and r, right? So what is this angle? This is 90 degree, right? Theta is 90.
Yes,
What would be sine theta? That is sine 90. This would be how much? 1. So if I calculate the small magnetic field dB at this point, so that would be how much? That would be mu naught by 4 pi and I dS sine theta is 1, right? And then r square, correct?
Yes, sir.
So now, if this is the small magnetic field, right? If we want to calculate the total magnetic field, then what we need to, if we want to calculate, this is the small magnetic field dB, right? So to calculate the full magnetic field, this is using the Bio-Savart's law, right? The Bio-Savart's law. This is the small magnetic field. What about the total magnetic field? How can you calculate that? If you are given a small x and then you want to calculate the whole x, then how do you calculate? Take the integral, right? Right? So you take the integral on both the sides. So integral on how much is this? This is integral of this is integral of mu naught by 4 pi I dl by r square. Can you tell me, is this r changing? Is this r changing?
Yes, sir.
This
No,
r.
sir. No, sir.
This is fixed. Mu naught is fixed. 4 pi is fixed. I is fixed. So
Hmm.
all these are constant. What is the integral of dp? That would be full d. That would be full
Hmm.
d. Because integral of dx is how much? X. Right? So this would be full magnetic field, and that would be mu naught by 4 pi r square, that is taken outside. I is also taken outside, and then dl. So this small length that we have taken dl, if you integrate this dl, so how much you will get? If you integrate this dl, what would be the total length that you will get? Yeah, if you add up all these dl, if you add up all these dl, then what is the distance that you will get? If you add up all these small dl, dl, add up all these dl, what you will get? Now, what is this shape? What is the distance that you are covering if you add up all these things? What is this distance? Circumference, right? Circumference of the circle, right? This is the circumference, right, Arslan?
Yes, sir.
So if you integrate this dl, you will get the whole circumference, and that would be pi. So this r and this r will cancel. This 2 pi will cancel this. So this would be mu naught I by that is the magnetic field at the center of a circular wire. Right? Is it clear? Is it clear?
Yes.
So we have calculated the magnitude, and we have to also show the direction. Right? So calculate the direction. Direction is given by modified Maxwell right hand. What is the modified right hand thumbs rule? So what was the right hand thumbs rule? In right hand thumbs rule, we calculated the direction of the straight wire, magnetic field due to the straight wire. So we placed our thumb in the direction of current, and then we curled our fingers, all the four fingers, and that direction was given by this magnetic. That was the Maxwell's thumb, right? Right, Arsalan?
Yes,
So now in this case, what is the modified Maxwell's right hand thumb rule? So in this case, we have to curl our fingers in the direction of the current, right? So if we curl our finger in the direction of the current, what is the direction that thumb is pointing out? What is the direction that thumb is pointing out? If you look at the screen, what would be the direction the thumb is pointing out? Yes, did you understand
sir.
that? Yeah.
Yes, sir.
So current is flowing in this way, right?
Hmm.
So current is flowing in this way. This is anti-clockwise direction. So if we curl our four fingers in the direction, what is the direction our thumb is pointing at?
So the direction of the thumb is, sir, along the direction of the current.
Along the direction. So the curl of the fingers, this is this direction. And if we put it in that way, so the thumb is pointing outwards. Did you see that? Let's say this is the current which is
Yes, sir.
this is the current. So current is flowing in this way. The current is flowing in this way, right? So if you your fingers, curl your fingers in this way, so your thumb is pointing outwards. Did you see that? Yes. Did you see that?
Yes,
Yeah. So you take the example of this diagram, right? If we curl our thumbs in this, if we curl our fingers in this direction, then the thumb is pointing outwards. So
yes,
can you tell me how do we denote the outward direction? By point or by cross? How do
sir,
we
by point.
by point? Good, absolutely right. By point everything. So magnetic field would be direction would be right. So if I write B vector, so this would be mu naught I by 2R and then dot. And we can also write k hat as well. This is one thing. So let me write this rule in here, right? So we have to curl our finger of the direction pointed by thumb is magnetic. Okay, so this is the Maxwell's modified Maxwell's thumb, right? And similarly, okay, so you please note it down, and then we'll talk about the other shapes as well, right? So please note it down, and then we'll talk about the other shapes.
Yes, sir, done.
Uh, Done. Okay, this part as well. On this part. Yeah, whenever you have voted, please tell.
Yes, sir, noted down.
Oh, you have already voted. Fine. Okay, so then we can have other shapes as well, right? One is this. So then we have semi, circular, wire. Right. So we have this kind of wire. So calculation, every calculation would be same, right? This is the R distance, right? This is the R distance, and this is dl. And let's say the current is flowing. This is the direction of dl. Again, the angle is theta is 90, right? So dB is simply mu naught by 4 pi I ds by r square. And if we integrate this thing, right? If we integrate this thing mu naught by 4 pi I dl by r square, so we will get what? Mu naught by 4 pi r square I. And if you integrate dl, so what you will get? What you will get? Yes,
Mm, sir, DL.
yeah, if you integrate dl, what you will get? In the previous case, you got the circumference of the circle. In
Yes, sir.
this case, what you will get?
Sir, the radius.
It is if you integrate this dl from if
Mm-hmm.
you sum up all these dl, right? What is the distance that you will get?
So that's a semicircle, right then?
Semicircle, yes, absolutely correct. In the previous case, we got the whole circle. In this case, we get semicircle. The perimeter of the semicircle, and how much is that? Pi r, right? So the half of semicircle, half of circle. Circle is 2 pi r. This is pi r by 2 pi r, right? Pi cancel, r cancels. Not I by 4. This is the magnetic field in the case of semicircle circle wire. Direction would be the same as you will use the so direction would be right. So this would be the magnetic similarly, we can have an arc wire. So arc wire is what? So you have bent a wire in this shape. So this is the arc. And let's say this is the arc of this circle. And then let's say this is the direction of the current, This is center, and this is the R, right? And DL is going in this way. So again, this is DL. So DL and R. Again, theta is 90. And then if you write this thing, right? So again, your magnetic field would be not I by 4 pi I dl by r square. And then again, you have to integrate. So B would be, I will write directly 4 pi r square and then dl. So now again, you tell me, here say I give you this angle, which is theta. So what would be this thing? What would be this thing? Yes, what would be this thing?
Uh,
What would be this integral?
square by r dl. So just
Just this arc length. So it
yes,
would
sir.
be
So just I like
I is the
half.
current. I is the current which is flowing, right? So arc length. And let us go back to our 10th standard. Arc length. How do we calculate? This is if this theta is given. This is the arc that we want to calculate, right? So this arc is given as the theta by 360 and 2 pi r. That is how we write the arc, right? So in this case, if I write 360, so this is in degree, right? Right? Clear? Is it clear?
Yes, sir.
Okay. So you remember this, right? You remember it. So then if I write this,
Yes.
this would be arc length. So this would be how much? Mu naught I by 4 pi r square. Arc length is theta by 360 and pi r square 2 pi r, right? Arc length is pi r. So remember, this is in degree, right? This is in degree. And then we can cancel this thing, right? So then we can cancel this thing, pi, and this is 2. And then this r and this r we can cancel. So this would be how much? So this would be mu naught I by r and theta by 3. So this theta is in degree, right? But if we write it in radians, so if we write it in radians, so this would be mu naught I by theta. And if we write 360 degree in radian, so how much is 360 degree in radian? How much is that? 360 degree in radian. How much is that?
So 60 degree in radian will be
Pi, right?
yes.
2 pi. So pi radian is 180. Pi radian, that would be 180 pi. Radian, yeah, we represent it in this way. This is, but we have to understand that these are in radians. This theta is in radian. Right? Remember, this is very crucial. So then we can write this thing as P as mu naught I theta, and this is how much? This is 4 pi. This is, and this theta is in radian. So either you can use this or you can use this. If it is given in degrees, so you have to use this. If it is given in radians, you have to use this. Clear? Yeah, is it clear?
Yes, sir.
Okay, then please hold what happened. Then please down this part, and then we'll do one question. And direction is same. Direction you have to use the modified version of the Maxwell's light. Have to. Whenever you have written, you have noted it down, please. And how is the cold there? How's the weather there?
Yes, sir, it's relatively cold here, sir.
Relatively
It's
cold.
not that much cold, but it's still somewhat cold.
In Delhi, it's pretty good. It's going 5 or 6. Okay.
Yes, sir.
Yeah. Okay. So now these parts as well. And this is very important. Whenever you are writing in degrees, this or whenever you're writing it. So generally people write it in this way, but we have to remember that this theta is in gradient. Just keep that in mind and then
Yes, sir, done.
okay. So let us do one question, and it will use all the properties that we have studied, all the shapes that question is so you have the current is flowing like this high current is, and this is let's say R, right? And at this P point, you have to calculate the magnetic. So this is one question. The other question is that you have to calculate the magnetic field. This distance is again R. The current is flowing in this. For both the cases, you have to calculate the magnetic at this P point. Okay, so what would be the answer for this one? How many shapes are there? For this case, how many shapes are there?
Sir, which case, sir? This one?
The first case, first case.
How many shapes are there?
Yeah. Yeah. So how many? If we break this thing, this
Hmm.
geometrical figure in different shapes that we have studied so far.
Then we
So
have line, semicircle, and then if we count that other line, then I guess a quarter circle.
yeah, so we have two lines and one semicircle, right? What does that mean? Not this line. This is the radius that I am telling, right? This is the flow of current. The current is flowing. So we have one line, semicircle, other line. So three, we have three parts. One, three, right? Right, Ursula?
Yes, sir.
Okay, so this is a straight wire, right? This is a straight wire, and this is the line of that straight wire, right? So this is line of that straight. And we are calculating the magnetic field due to this straight wire at this point along the line. So P1 would be how much? How much would be if we calculate the magnetic field along the line of straight wire? So how much is that? Ah, so you have gotten that part. Let me just revise that part for you, right? We studied that whenever this is the flow of the current, and if we calculate the magnetic field along the line of current, that is how much? Yes, that is zero, right?
Yes, sir.
So this P1 will be zero. So if P1 is zero, then have to bother about this one. Then what about this is one, and then what about V3? So this is the current which is flowing, and we are calculating the magnetic field at P point. So again, V3 would be zero because V1 and V3 are straight wires magnetic field along the line. So these are zero, right. So what is the only shape that is contributing? This is the semicircular shape wire, and we know that for semicircular wire, magnetic field is how much? Not I by 4. This is the magnet. What would be direction? What would be the direction? What would be the direction
Sir, direction would be like along the wire.
along the wire?
So right
Right.
or
So
straight?
what is the main method to calculate the direction? What is the method?
Mm-hmm.
Method is modified Maxwell's thumb, right? So we have to place our right hand and curl our fingers in the direction of
Yes, sir.
the. What is the direction that you are getting?
Circles.
Yes. So magnetic field is going this way, right? So this
Hmm.
curl it, so it is going outwards, right?
Yes, sir.
This is outward, so I can write it as K. I can also write it as point, but yeah, K hat I can also write. So this is this. Now again, similar thing about the second. So in second figure, this is again 1 and the current is flowing I, I, and we are calculating magnetic field at circuit, right? So again, V1 equal to V3, that is again same case. This is 3. But V2 is again due to semicircle magnitude would be mu naught I by 4R. And can you tell me what would be the vector? This is mu naught I by 4R magnitude. What is the direction? What is the direction that you get?
Sir, direction would be for
Inwards or outwards?
sir outwards.
If you curl your finger in the direction of the semicircular wire, right, the current,
Yes, sir.
what is the direction you are getting outwards?
But so can you like show me a visual representation of it? Because we're using the right hand thumb rule, right, for this,
Yeah,
sir.
so this
Yes, sir.
is,
So how will that work? How will it go inwards, sir? Like the thumb rule?
so your current is going in, this is the direction. Right?
Yes, sir.
So if it is going in this way, so what is the direction that you will
Inwards.
get? Right. So if it is going in this way, then it is outward. If it is going in this way,
Inwards.
we are getting inward direction, right? Okay, so this is inwards meaning minus k at direction. So PP, what did I press? Yeah, so PP minus naught I by 4R. These are the two situations. Please note it down, and then we will talk about the other law. So Bio-Savart's law we have done, right? Then we move on. There's other thing as well, right? So magnetic field due to the axis on the axis of the wire, but that part will not be concerned. Okay, just quickly note it down and then study about the next law. Whenever you have noted it down, please tell.
Yes, sir. Johnson.
Done. So the next property or next law, which is used to calculate the magnetic field of different kinds of wire, is the Ampere circuit, right? Prominent one, right? Widely used. Both the laws have their pros and cons, right? Ampere. What does this law state? It states that the closed line integral of magnetic, or it says that the flux side, so it states that the line integral of magnetic field side and ampere is directly uh, the current enclosed by the line integral or right. And if we remove that proportionality, so it comes out to be this shows that this is a closed loop, and then this is V dot dS, and this is directly proportional to I enclosed. And if we remove this proportionality, so this we got this thing which is mu naught I. So this is what we call the Ampere circuit, or sometimes it is also called Ampere circuit. Right. So there is one peculiar thing about this thing, right? This represents the closed, right? So if we have a line, right? If we have a line, and if we close that line, so the shape that it makes, so that will make a closed loop. So this is the closed loop, and this dot dl is the line integral, right? Line integral of magnetic. So this is your Ampere circuital law or Ampere's law. And there's one important thing which is Amperian, right? So this Amperian, where Amperian uh, follows either of follows one of the properties. Any one of the following properties. So one would be that inside the Amperian V dot V and dS are perpendicular, or We can also have B and BL are parallel. Or the third one is that inside Amperian B vanishes or B is zero. So these any of these three properties this Amperian follows, right? So this is all about this Ampere circuit law, and this is very important. So using this Ampere circuit law, right, we calculate the magnetic field of different kinds of material. So let me say that let me also talk about this closed, right? So the closed will make an open circuit, right? So do you remember? Remember the Gauss law? Remember the Gauss law.
Yes, sir.
So in Gauss law, what kind of what was the Gauss law? Do you remember it? What was the Gauss law? So let
Yes,
me.
sir. I think so. I remember it a bit.
What was the Gauss law? This was this is the Gauss law, right?
Yes, sir.
So in here also you got this closed loop, but this loop was for the closed surface. So in this one, this surface is closed like a sphere or like whatever, like a cylindrical thing which is closed. So those kind of shape, the closed, or let's say you have a cube. So those are closed shapes, right? The surface are closed. And if I talk about the disk, so the disk is a closed surface or open surface. Can you tell me that? What kind of surface is that? Open or closed one?
Sir, close.
Closed. So is the surface of this disk closed? We have this disk. So is it closed? It is open from either sides, right?
Yes, sir.
The surface is not closed. If you have let's say sphere, sphere has this closed surface, right? Disk does not have a closed surface. These kind of shapes are called open surface. This is open surface. So for open surface, you will get this line, outer line. So you will get a closed loop of line. So you get a closed line, right? For open surface, you get a closed line. So let's say if I have this wire, right? So let's say I have this wire and I make a closed loop of the surface that you got. That this is a circular surface, right? This surface is the open. So if you close a line, then you get an okay. So yeah, these are some very important things to remember. And okay, so please note down this thing, and then we'll study about the application of this.